Hi guys, so today we're going to be talking about equilibrium. So, as you may know, this is a really big part of the AP Chem curriculum. So, make sure you understand the basics of it at the beginning that I'm going to teach you here before you start moving on to the next chapters with buffers and solubility and stuff like that. So, the definition of equilibrium is the state where the rate of the forward reaction is equal to the rate of the reverse reaction. So, when equilibrium is happening, the concentrations of all the reactants and products are remaining constant, but it's not to be confused with them being equal. They are not necessarily equal, but we'll talk about that a little bit later. With time, once equilibrium has been established, and this is at constant temperature. So you see the graph over here. This is a graph of the time and concentration. So you can see that there's a time where the concentrations of the reactants, which are A and B, are equal to the concentrations of the products. But eventually the products supersede that, and then they are at this TE, which is the equilibrium, that when the time when equilibrium is established, the concentrations level off and they become constant. So the graph represents how concentrations do not necessarily have to be equal, they just have to be constant when equilibrium is established. So the equilibrium constant, which we call K, is it numerically determines what is in the beaker at equilibrium. So here's the equation down here. Kc, and we'll talk about Kc or Kp, the different subscripts that you can have, is equal to the concentration of the first product to the coefficient of the balanced reaction, and the other product to the coefficient over the concentrations of the reactants to the coefficient of the balanced chemical equation. So molarity of the products and reactants raised to the power of the coefficients of the balanced equation, exactly what I just said. So more things about the equilibrium constant are Kc, or KeQ, it's sometimes written, is used for aqueous solutions. So that's when you're going to use concentration like I talked about in the last slide. Kp is used for gases, but instead of concentrations, it's going to be the pressure, the partial pressure of that gas raised to the power of the coefficient. So this is not to be confused with kinetics, where you use your initial concentrations and with order just completely wipe kinetics from your mind, because now we're talking about the equilibrium coefficient, which is different than the rate constant. So if the reverse reaction occurs, it would be the reciprocal of the K value. So the K of the reverse is equal to the 1 over K of the forward reaction. So if there are multiple of the same reaction going on, you multiply the K values to the n power, which goes off of this rule of if you're adding the reactions, you just multiply the K values. So that's just kind of something you have to memorize, but it's not too tricky. So using K. When you use K and calculate it, you're only using aqueous or gaseous solutions. You do not put the solids. If there's a solid, if it's a precipitate reaction or it produces a liquid, you do not have those in your equilibrium expression. So if you have all your products are either liquids or a solid, then you just do 1 over the concentration or partial pressure of your reactants raised to the powers. So relationship between Kp and Kc, this is just a simple equation. Kp is equal to Kc to the RT delta N, and delta N is the moles of gaseous product minus moles of the gaseous reactant. So Kp, like I said before, is for when you have partial pressures and you're using gases, and Kc is when you have aqueous solutions. And R, don't get confused, there's two different R values you're bouncing back and forth between, and R is 0.0821, so just remember that. So equilibrium can be disturbed by either adding or removing a gas reactant or product, and that would change the concentration or the partial pressure. You can either be compressing or expanding the system, which would clearly change the pressure or concentration, and a change in temperature. And we'll talk more about temperature when we talk about Le Chatelier's principle. Thank you.